Cool. So I'll just go in order. I think this is the order that it shows up in the test as well. It's like every other question. So this first one is, I don't know if anyone got this one right, so I'll make sure to explain this one. So for this one, it says, we have two people, Charles and Erica. They each have a bag that contains one marble of each color, and there's 5 different colors. And then what happens here is Charles will randomly take one marble from his bag and put it in Erica's bag. And then Erica randomly picks one marble from her bag and puts it into Charles's bag. So then the question is saying, what is the probability after this exchange that Charles's bag contains exactly one marble of each color? So if we think about this, in the first step, Charles will take a marble. It's going to be one of those blue, yellow, purple, red, or green colors. It doesn't really matter which it is. So you can kind of see that if it's blue, it kind of is the same case that if it's yellow. So we could say without loss of generality that it's like, let's say it's blue. So then in the second step, Erica will randomly take one marble from her bag and put it into Charles's bag. And so when Erica does that, she has one of each color plus one of some other color that Charles puts in. We could say that's blue, or we could say it's another color. In order for Charles's bag to contain exactly one marble of each color afterwards, that means Erica needs to pick one of the marbles that is the same color. So basically, Erica's bag has 6 marbles, 2 of which are the same color, and then the other 4 are distinct. So in this case, that means Erica will choose, basically there's 2 marbles that she could choose to make it happen out of 6 total. So the answer is 1/3. So there's not a lot of like calculations that you need to do for this one. This is more about like thinking through the word problem and turning it into a probability. Does anyone have any questions about that explanation?
Miss Wendy, could you please go over that again? I'm not sure I quite understand.
Yeah, so, okay, so Charles has 5 marbles in his bag. Let's say we have blue, yellow, purple, red, green. And then Erica also has blue, yellow, say Charles. Purple, red, green. So it says Charles randomly selects one marble from his bag and puts it into Erica's bag. So let's say Charles takes blue and puts it into Erica's bag. Then after that step, Charles will have yellow, purple, red, green, and Erica will have blue, blue, yellow, purple, red, green, right? And so in the second step, basically it says Erica then selects one marble from her bag and puts it into Charles's bag. So that means Erica will have one of 6 total choices. And then we have to see out of those 6 choices, which ones would result in this outcome of Charles's bag contains exactly one marble of each color. So the only way Charles's bag would contain exactly one marble of each color is if Erica selects one of the blue balls. Because if she selects any of the other balls, then Charles will have more than one marble of one of the other colors, and he won't have a blue marble. So that means there's 2 choices out of the 6 that Erica could randomly select that would result in the outcome that we're looking for. And here we, the other important thing here is like we looked at Charles, supposedly that he took a blue marble. And so we could recognize that it doesn't really matter which marble Charles takes. It's the same in each case. So we could use this term like without loss of generality. To say without loss of generality, say Charles takes the blue marble because it's kind of equal in each case. And so we could just, with this, note that the answer is 1/3. The other way you could do this is if you don't want to use this concept, you could say, okay, Charles has a 1/5 chance of taking the blue marble. And if Charles takes the blue marble, then Erica has a 1/3 chance of then picking the blue marble and giving it back to Charles. Similarly, Charles has a 1/5 chance of taking the yellow marble, and then Erica will have a 1/3 chance of giving the yellow marble back. And so on, and you're gonna have 5 of these, which will still give you 1/3. Any other questions? Or is there any part of that that wasn't clear? All right. Let's move on to the second question. So this one says, let S be the set of permutations of the sequence 3, 4, 5, 6, 7, 8, for which the first term is not 3. A permutation is chosen randomly from S. What's the probability that the second term is 4? So for this one, again, we want to recall our definition of probability, where we can count the number of sort of desired outcomes over the number of total outcomes. So we start with, so let's say probability second term is 4 equals number of permutations of S where first term is not 3 and second term is 4 over number of permutations of S where first term is not 3. Does everyone see why that's the case? This is just applying the definition of probability here. All right, so now let's calculate the top and the bottom. We start with the bottom, number of permutations of S where the first term is not 3. Does anyone have any ideas about how to count that?
You could take the first term as a variable.
Sorry, say that again.
You could take the first term as a variable like n, and you could say that for n there are 2 choices, that's 1 and 2 to find n.
I'm not sure I fully got that, but I think if you're saying, let's see how many choices there are for each term, that's like on the right track. So basically we have 6 numbers here that we want to permute. And we have the restriction that the first term cannot be 3. So that means the first term, there's 5 choices because it could be 4, 5, 6, 7, or 8. For the second one, we have 5 choices as well because it could be any number that we haven't already chosen, or it could be 3. For this one, we have 4 choices because it could be any number we haven't chosen. This one could be 3 choices, 2 choices, and then this one's sort of whatever number we have left. So here we have 5 times 5 factorial. The other way you could think about this is when we have a restriction for the first choice, there's 5 choices, and then we have no restrictions for the other 5 numbers, and there's 5 numbers left to order, so 5 times 5 factorial. What about for the numerator? Does anyone have any ideas on how to count that one? So we can use the same type of reasoning here. So for the first, basically, for the first term, we still have the restriction that it can't be 3, but now that we know the second term has to be 4, there's actually only 4 choices here because it could be 5, 6, 7, or 8. And then for these 4, we can permute the remaining 4 numbers, basically not the first number and not 4, but any of the other numbers in any order we choose. So that's going to be 4 factorial. So the numerator is going to be 4 times 4 factorial. And then if we simplify this, we get 4 over 25. Any questions on this one?
Yes, the numerator, you said the probability is number of permutations of S where the first term is not 3 and the second term is 4. And the denominator is the number of permutations where the first term is not 3. So why didn't you add the 5 times 5 permutation to 4 times 4 permutation?
So the 5 times 5 factorial is this, this quantity is 5 times 5 factorial. And then this quantity is 4 times 4 factorial. So instead of adding, we want to take the ratio to find the permutation. I'm not sure, was that your question?
Yes.
Did that answer your question?
Yes, please.
Okay, cool. All right. Any other questions? All right, let's move on to question 3. So this question says, what's the probability that an integer in the set 1, 2, 3, all the way to 1,000 is divisible by 2 and not divisible by 3? So any ideas on how to do this?
You can divide 1,000 by 2 and subtract it from 1,000 divided by 6.
Okay, so yeah, that's roughly what you want, one step that you want to do, but starting at the beginning, if we want to calculate the probability that a random integer that we pick is divisible by 2 and not by 3, let's say the integer we pick in, let's call this S. Then we want number of integers in S that are divisible by 2 and not by 3 over number of integers in S, right? And then we know the bottom one is just 1,000. That one's easy. And so then what you're suggesting is, how do we count this top quantity, right? So in order to count that, the suggestion was we basically count the number of integers that are divisible by 2. And we can do that by dividing by 2 and rounding down, but in this case, it divides into it exactly, so we get 500. And then we have to take out the numbers that are divisible by 3. And so we notice that the only numbers that are divisible by 3 and divisible by 2 are the numbers that are divisible by 6. So to get the number of integers in S that are divisible by 2 and not 3, that's the same as number of integers in S that are divisible by, 2 minus number of integers divisible by 6, right? And so this is 500, and then this is, we round down once we divide 1,000 by 6, which is 500 minus, I think this is 166. So this gives us 334. So then if we go back to this, we can plug this in and we get 334 over 1,000, which we simplify to 167 over 500. Any questions on this one? All right, we'll move on to the next question then. Okay. So this one says a fair die is rolled 6 times. What is the probability of rolling at least a 5 at least 5 times? So that's a lot of 5s. So when we have a fair die, it means, so usually a die has 6 faces, 1 through 6. And so, and fair means that you have an equal chance of landing on any face. So basically the probability of rolling a 1 is 1/6, probability of rolling a 2 is 1/6, etc. And then all the way to 6 is 1/6. That's what it means to have a fair die. And so first let's think about for one roll, what's the probability of rolling at least a 5? Can anyone answer that?
Would that be 1 out of 3?
Right, yeah. So if we want to roll at least a 5 once for one roll, then that means you have to roll a 5 or a 6. So that's 2 outcomes out of 6 total outcomes. So that's 1/3. Cool. Now we can look at this at least 5 times if we roll the whole thing 6 times. So what are the different ways that we could roll? Like say we have a sequence of rolls that we write down. How many different ways can we roll at least a 5 at least 5 times? So one way is say we roll at least a 5 all 6 times. So the first roll would be greater than or equal to 5. The second roll would be greater than or equal to 5. Third roll would be greater than or equal to 5, and so on. So all of them are greater than or equal to 5. The other possibility is we roll at least a 5 only 5 times. So basically that means we have, let's say 5 rolls that are at least 5, and then one roll where it's 4 or less. And if we had this, there's actually 6 ways, or 6, choose one, that this could happen. So basically it could be the first roll where you roll a 4 or less, and then the other 5 you roll 5 or more. Or it could be the first roll you roll 5 or more, and then the second roll you you roll less than or equal to 4, and then the rest you roll 5 or more, and so on. So basically we can think of it as out of the 6 rolls, we could choose one of them to be the roll that's less than 5. So basically we've divided this into 2 cases. So this is casework here. And so I'll call this case 1 and this case 2. So in the first case, let's calculate the probability that we get at least a 5 exactly 6 times. So anyone want to take a stab at that? So we know that the probability of rolling at least a 5 one time is 1/3. And then the other thing we know is that every time we roll the die, it's independent of what we got the previous time. So if it's the probability 1/3 that we roll at least a 5 once, then the probability we roll at least a 5 twice is going to be 1/3 times 1/3. And so in this case, the probability that we roll at least a 5 all 6 times is going to be 1/3 raised to the power of 6. Does everyone see why that's the case, or are there any questions about that before I move on? All right, let's do case 2. So here we want to calculate the probability we roll greater than or equal to 5 times and less than or equal to 4 one time. So remember, the probability that we roll greater than or equal to 5 is 1/3. So the probability we don't do that, or the probability that we roll, is 2/3. So if we want to calculate this, what formula or what expression would you use?
You multiply them.
Yeah, so because there's, we want to say roll greater than or equal to 5 times, we want to multiply 1/3 5 times, and then 2/3 one time. And then we need to take into account all the different ways in which this could happen, right? So I mentioned earlier, there's 6 different ways where we could roll greater than or equal to 5 and a less than or equal to 4 in order. So basically I could first roll the 4 or less, or I could roll that second or third or fourth or fifth or sixth. So we also have to multiply this by 6 because there's 6 different ways that this could happen. So now we can put it together. The probability of rolling greater than or equal to 5 at least 5 times equals the sum of the probabilities in the 2 cases, because it could either be case 1 or case 2. So that's going to be 1/3 to the 6th plus 1/3 to the 5th times 2/3 times 6. So if we expand this out, this is going to be 1 plus 2 times 6 over 3 to the 6th, which gives us 13 over 729. Any questions on this one?
Yes, for the case 2, you did 1/3 all raised to the power 5. So for the case 1, why didn't you also do 1/3 all raised to the power 5 times 6?
Are you talking about case 1?
Yes.
Because there's only one way that you can roll greater than or equal to 5, kind of in order. Basically, there's every roll has to be greater than or equal to 5. For case 2, you could actually like think about it maybe in some cases, right? You could have, so for your 6 rolls, you could have greater than or equal to 5, greater than or equal to 5, and then the last one could be less than or equal to 4. Or you kind of have the same, but the second to last one is greater than or equal to 4. Or maybe this one's less than or equal to 4, and these are the same. Or this one's less than or equal to 4, and these are the same. Or this is less than or equal to 4, and these are the same. Or this is less than or equal to 4. So there's actually 6 different cases here, and for each of the cases, the probability that this happens is here it's going to be like 1/3 to the 5th times 2/3. Here it's going to be the same, right? It could be 1/3 to the 4th times 2/3 times 1/3. Here it's 1/3 to the cubed, right? 1/3, 1/3, 1/3, 2/3, 1/3, 1/3. And so on. And so we just sort of took a shortcut here by using combinatorics to say, oh, there's actually 6 ways that we could do this. So to calculate the probability of all these cases together, we can just take the probability that we get 5 rolls of greater than or equal to 5, probability that we get 1 roll of less than or equal to 4, and then we multiply that by the total number of ways that this could happen. But if you were to sum all of these, right, you're going to get the same number, which is 1/3 to the 5th times 2/3 times 6.
Okay, thanks.
Yeah, no problem. Good question. Any other questions? All right, let's move on. So this one's also a bit tricky. This is a word problem here. Melinda has 3 empty boxes and 12 textbooks, 3 of which are math textbooks. 1 box will hold any 3 of her textbooks, 1 will hold any 4 of her textbooks, and 1 will hold any 5 of her textbooks. If Melinda packs her textbooks into these boxes in a random order, what's the probability that all 3 math textbooks end up in the same box? So there's a couple different ways you could count this, but first let's break down the problem. So basically she has 3 boxes. 1 box holds 3 textbooks, 1 holds 4, 1 holds 5. So one first thing that I would notice here is that if 1 box holds 3 textbooks, 1 box holds 4 textbooks, and 1 box holds 5 textbooks, that means that there's a total of 12 textbooks, which means all of the boxes will be filled. There's no sort of like empty space in the box. And then we have 3 math textbooks. So maybe we say 3 of her books, we'll label them as M. And then we have 9 non-math textbooks. So maybe we just call those like T for other textbooks. So now we've represented her textbooks. And then we can also think about what it means to be putting things in her boxes. And so since 1 box will hold 3 textbooks, maybe we say, okay, we have box 1 that has capacity 3. Let's do this. Box 1 that has capacity 3. Box 2 that has capacity 4. And box 3 that has capacity 5. And so now we want to see what is the probability that all 3 math textbooks end up in the same box. And since we have 3 boxes here, this lends itself well to casework, where we could say the probability that all math textbooks are in the same box, that equals the probability that, I'll just write this out for clarity, probability that all math books are in box 1, or all math books in box 2, or all math books in box 3. And so if we use our kind of probability rule of sum here, since these are different cases, with ORs, we could basically say this equals the probability that all math books are in box 1 plus the probability all math books are in box 2 plus the probability that all math books are in box 3. Did everyone see why that's the case? If so, then we can start calculating probabilities. Cool. So let's calculate these probabilities. So in the first case, we have all math books in box 1. And so we want to count the number of ways that that could happen over the total number of ways that Melinda could put her textbooks. So going back to up here, we know there's 12 slots for boxes. And so this lends itself well to sort of a stars and bars kind of thinking. So, but also we don't really need the bars because we already have the fixed, like the fixed number of books in each box. So we can think about how many ways can we arrange sort of 3 math textbooks and 9 non-math textbooks into these 12 slots such that all math books are in box 1. And so for this one, it's kind of straightforward because there's only 3 boxes that can, 3 books that can fit in box 1, and there's 3 math books. So there's actually only one way that you could do this. You could basically put all the math books in box 1 and then all the other sort of T textbooks in the rest of them. And so in that case, there's basically one way that we could put all the math books in box 1. But for the denominator, we want to count how many total ways there are for Melinda to distribute 3 math books and 12 non-math books. And to simplify, we've kind of decided that these math books are indistinguishable and these non-math books are indistinguishable. And so here, that simplifies down to the problem of how many different orderings do we have of 3 M's and 9 T's. So if you all remember that, it's going to be 3 plus 9, choose 3, which is 12, choose 3. Any questions on that before I move on to case 2? All right, so for case 2, basically we want to compute the probability that all math books are in box 2. So we actually have the same denominator. It's 12, choose 3. But what about the numerator? Any ideas on how many ways we could do that?
Could it be 5, choose 3? I think I start posting the yachts.
Why is that?
4, choose 3 because there are 4 capacities and you need
Will
to
it be
put 3 books.
will it be 12 choose 4?
Why do you say 12 choose 4?
Because there will be 12, like you did in the previous thing, there will be 3 math textbooks and 9 other textbooks. So when you add them together, you get 12 books, and then choose 4 because 4 of those textbooks will be chosen to be in the box.
I see.
But
So
would
that's
it
the
rather be
total
12
number
choose
of ways
3?
that you could choose. If you had 12 different books, that's the total number of ways that you could choose 4 of them. But in this case, we want to ensure that box 2 has all 3 math books. And so if we think about this, where let's assume the ordering matters, but the books are indistinguishable, then there's actually, the first suggestion was right. There's actually 4 choose 3 ways, because basically we need to figure out how to put 3 math books in 4 spots. And so basically you could have math, non-math, math, math, or math, math, non-math, math, or math, 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 non-math, or non-math, math, math, math. So there's four ways. So this gives us 4 over 12 choose 3. And then lastly, there's a case where all math books are in box 3. And here we have a similar approach. So basically now we need to distribute 3 math books among these 5 spots we have in box 3. And so that's going to be 5 choose 3 over 12 choose 3. And so now we can plug this back into our original formula here. So the probability equals 1 plus 4 plus 10 over 12 choose 3. So this equals 15 over 12 times 10, 11 times 10 over 6. So it equals 15 times 6 over 12 times 11 times 10. We can simplify this. So this gives us 2 on the bottom, 3 on the top, 2 on the bottom. So this gives us 3 over 44. Any questions on this solution? So one thing I'll note here is there's different ways that you could compute this probability. In this case, I decided to simplify the problem a bit by kind of taking the case where the other textbooks are indistinguishable and then the math books are indistinguishable. And I think that actually makes the counting a lot easier. But you could also count, like, what if the math books are distinguishable? Or what if the order in the boxes doesn't matter? And so all of those would give you the same probability, but here it's about transforming the probabilities and the quantities that you need to count into something that's really easy to count. So there's actually multiple solutions to this problem. And so this is only one of them. All right. Any questions before I move on to the last one? Okay. So here we're back to dice rolling. But here, instead of a fair die, we have we're saying kind of weird pair of dice where the probabilities of rolling 1, 2, 3, 4, 5, and 6, they're in a ratio 1, 2, 3, 4, 5, 6. So when we have a fair die, the ratio is 1 to 1 to 1 to 1 to 1 to 1 because it's all the same. But here, we're more likely to roll a 6 than we are to roll a 1. And so the question says, what's the probability that we roll a total of 8 on the 2 dice? So there's a couple steps to solving this problem. The first one is let's compute the probabilities of rolling a 1, a 2, a 3, a 4, a 5, and a 6 given this ratio. So any ideas on how to do that?
Yes, it would be that number's amount out of the addition of the whole ratio. So for 1, it would be 1 out of 21.
Cool. Yeah. So I'll just write this down. Step 1, we want to compute probabilities of rolling and so you said the probability of rolling a 1 is 1 over 1 plus 2 plus 3 plus 4 plus 5 plus 6. And that is 1 over 21. Probability of rolling a 2 is 2 over 21. Probability of 3 is 3 over 21. Probability of 4 is 4 over 21. And so we can kind of check, sort of gut check this, right? The probability should sum to 1 because you have to roll 1 through 6. So if we sum it, we get 21 over 21. And then we can also kind of check the ratios are right? So if you take the ratio of the probability of 1 to the probability of rolling 2, you get 1 to 2. And so the ratio you get is 1 to 2 to 3 to 4 to 5 to 6. Cool. So now we want to compute for step 2, now that we know the probabilities of the individual, rolling individual numbers, we want to compute the probability we roll an 8 in total on 2 dice rolls. So how many ways can we roll a total of 8? Or maybe I shouldn't say how many ways, but what are the ways that we could roll a total of 8?
If we have the first one is a 2 and the second is a 6, for example.
Okay, cool. That's one case. How else could we do it?
Sorry, if there's a 3 and a 5.
Mm-hmm.
And if both are 4.
Okay, cool. If we remember we have 2 die, right? There's actually sort of a higher chance that we get, say, 3, 5 than 4, 4, because we could say the first die roll could be a 3 and the second could be a 5, or the first die roll could be a 5 and the second one could be a 3. Similarly, the first roll could be a 2 and the second roll could be a 6, or the first roll could be a 6 and the second roll could be a 2. So these are the total cases. So just to be explicit about this, probability, we get a total of 8 equals the probability we roll a 2, then a 6, or the probability we roll a 3, then a 5, or 4, then a 4. Or a 5, then a 3. Or a 6, then a 2. So now we have 5 different cases. So we want to calculate the probability that each of these happens. So what's the probability that we roll a 2 and then we roll a 6?
12. It's 12 out of 21.
Why is that?
Because the probability of rolling a 2 is 2 out of 21. And the probability of rolling a 6 is 21. 6 out of 21. And then when you multiply them together, it's 12 out of 21.
Cool. So it's not 12
Yeah.
over 21, it's 12 over 21 squared. But yeah, we want to multiply them together. We want to multiply them together. Cool. So we could do the same idea for 3, 5. So what's the probability we roll a 3 and then a 5?
Three out of 21 times 5 out of 21.
Yep, that's 3 out of 21 times 5 over 21. So that's 15 over 21 squared. And then what's the probability we roll a 4? Then another 4.
4 over 21 all squared.
Yeah, so it's 4 over 21 squared. So it's 16 over 21 squared. Cool, we're almost done. What's the probability we roll a 5 and then a 2?
It's the same as the probability of rolling a 3 and 5.
Yeah, oh, sorry, yeah, 5 then a 3. So it's 3. 5 over 21 times 3 over 21, that's 15 over 21 squared. And then the last one is probability roll a 6, then a 2. That equals the first one we calculated, 6 over 21 times 2 over 21, which is 12 over 21 squared. So let's go back over here and plug it in. So the probability we get a total of 8 is the sum of all of these probabilities, because if any of these happen, then we get a total of 8. So if we sum this up, we get 12 plus 15 plus 16 plus 15 plus 12 over 21 squared. And if we simplify this, the top we get 70, bottom is 21 squared. We can see that both of them have a common factor of 7. So this becomes 3 times 21. So this becomes 10 over 63. Any questions on this problem? All right. And then I guess, but before we move on from combinatorics, did anyone have any questions about just any of the lecture material from earlier this week or any of the homework? All right. I'll pass it to Matthew then, who will go over the other problems on the test.
Okay, let's take a look at some geometry problems. Okay. first problem, we've got an arbulos. That's what we call that shaded region. We have an arbulos cut out of a circle. We want to know the ratio of the shaded region to the non-shaded region that's inside those little circles. So, let's see, do we have a radius here? If each small circle has radius 1. Okay, so we have a big diameter of 2. I'm going to copy this here, make it a little bit bigger for us. So this whole big radius is 2. So I'm just going to go ahead and compute the whole area. The big circle has area 4 pi. And then each one of the little circles with radius 1 has area pi. And if each one of those has area pi, then we have 4 pi minus 2 pi left over, but the shaded region is half of that. So the area of the shaded region is pi, and the ratio of that area to the area of one of the smaller circles is pi to pi, which is just 1. Any questions or thoughts about this one? Okay.
Mr. Crawford,
Yeah.
since you said express it as a ratio, wouldn't it rather be 1 out of 1?
You know, if you want to, yeah, it would be perfectly reasonable to express this as 1 to 1 if you want that ratio format. You know, when I think of ratio, or, you know, when a lot of people think of ratio, a number, like a common fraction will suffice. You know, 3 over 2, we can call a ratio, or we can say 3 to 2. And yeah, some people may call this like ratio form or something like that. But, you know, we're asking for the ratio, not for a specific form. So I think either one of these I would find perfectly acceptable.
Okay, thank you.
All right, number 3. Okay, how many square units in the area of the region inside the circle but outside the triangle? Kind of starting backward. I do that sometimes with wordy problems. Anybody else do that? Maybe that's a habit from years and years of looking at wordy problems. It's easier for me to read for the details when I do. So that green area is what we're looking for. And we've got this circle and it's drawn. Now it kind of looks like this, these two sectors, the green sectors, are 90-degree sectors. But is that true? How do we know?
Because the triangle is an isosceles right triangle.
Well, the big triangle is an isosceles right triangle, but you know the question is, how do we know that like this point right here, is that in the middle of AB? Is that the midpoint?
Well, yeah, because the circle is tangent to the triangle.
The circle is tangent to the triangle at the midpoint of the hypotenuse. So here's what I'm going to point out. It seems like it's probably true that these are midpoints, but what if we were to take the square made up by the midpoint of AB, the midpoint of BC, B, and P? If we were to draw that square, and then draw in the diagonals that bisect each other, well, then we have 4 equal lengths. And so if we draw a circle with that radius, then that circle does go through B and it's tangent to the hypotenuse at P. So this is what we're talking about. So we are looking for the sum of the areas of 2 90-degree segments. Okay, well now we need the radius, don't we? Or do we? Is there a way to do this without the radius? Oh, you know what? AC is 8. So that's 4 and that's 4. And we've got, you know, we can kind of tile this with these triangles with hypotenuse 4. And that means that the radius of the little circle is 2. Okay, we have a radius of 2. So each 90-degree segment is going to have area 2 squared pi times 90 degrees over 360. That's the area of the sector. And then from that, we subtract out the area of one of those little triangles, but we have 2 of these. So we have 2 times 4 pi times 1/4 minus 2. So overall, it looks like we're going to get 2 pi minus 4. Any questions or thoughts about this one? I bet some people solved this in different ways. Did anybody use the Pythagorean theorem or like an understood ratio of the lengths of the sides of an isosceles right triangle? Okay. So no other offered solutions here. I think tiling helps. I think there are a number of ways to go about this, so long as we know how to find the area of a segment. And now let's take a look at number 5. We have this nice, pretty diagram here. A flower. At the very least, we have a bunch of petals, and each petal is 2 segments. So ultimately in this problem, we're trying to find the area of 12 segments. And fortunately, they are all same size. So we've got a radius of 3. Okay, so that's 3. And you know, when we take a regular hexagon is actually 6 equilateral triangles smushed together, right? Because we wind up with a 60-degree internal angle in an isosceles triangle because those radii are the same, which means that the equal base angles wind up being half of the remaining 120 degrees. So we have equilateral triangles all the way around. And each of these segments, therefore, is a 60-degree segment. So its area is going to be 1/6 of the area of a circle with radius 3 minus the area of the equilateral triangle. And I think did we derive that formula the other day?
Yeah.
Yes.
And then we multiply all of that by 12. And the 12 and 1/6 turn into 2. We wind up with 18 pi minus 12 takes out the 4 with an extra factor of 3, so 27√3, if I have done my arithmetic correctly. Any questions or thoughts about this one or other methods? All right, let's take a look at number 7. Measure the angles formed by clock hands at 11:10. So put 12 up there, 1, 2, 3. I'm not going to fill in the whole clock because we really only need the top parts. And then I'm actually going to start the clock at 11. And I want to think about what happens as the hands move from here, because I don't know about anyone else, but it's a little bit easier for me to think this way. The big hand is going to move over here, and that's going to open it up 60 degrees. Maybe I'll do that to show the final position. It's going to open up 60 degrees. We start out with a 30-degree angle with 1/12 of the circle. And then the smaller hand moves more slowly. In particular, the speed of the smaller hand is 1/12 of the speed of the longer hand. So if the longer hand moves 60 degrees, the smaller hand moves 5 degrees. So while the angle opens up 60 degrees wider, it also closes down 5 degrees at the same time. So we can compute the measure of the angle as 30 plus 60 minus 5, which is 85 degrees. And this is just one of many ways to do this problem. Who else came up with a different solution than this?
I did not think that the tiny part that the hour hand would move, I did not add that to my equation, so I ended up getting 90.
Yeah, me too.
Right. Yeah. That, if the small hand stayed stuck at 11, then that would be the case. You know, and I bet a lot of people thought about this in terms of rates, like how many degrees does the clock move per minute? Did anybody solve the problem that way? How many degrees does the minute hand, how many degrees does it move every 1 minute?
6 degrees.
6 degrees. And how many degrees does the hour hand move per minute?
.5 degrees.
That's right. It moves 30 degrees every hour. So per minute, we divide that by 60 and we get 1/2 of a degree per minute. So one of the hands is moving away at 6 degrees per minute. The other one's closing at 1/2 degree per minute. So they open up at 5.5 degrees per minute. So over a period of 10 minutes, the angle opens up 55 degrees. So 30 plus 55 is 85. So that's a second way to look at it. And I bet that that's probably the more common way. Maybe, I don't know. Anyhow, let's take a look at number 9. Whole bunch of ways to do this, but I'm going to do something a little bit. Oh, you know what? Yeah, this is interesting. I probably should have asked the problem differently. Hey, Wendy, are you still there?
Yeah.
We should probably accept 2 answers on this. We should probably accept both 360 and 720.
All right, I'll take a look to see if anyone gave that one. I know a lot of people did put 360.
Okay. I probably should have said, find the sum of the exterior angles of of a convex quadrilateral, I should have added 1 angle per vertex. So if you thought about something like this and you said, hey, there's an exterior angle here and an equal exterior angle there, and you counted 2 per vertex, that's going to be fine. That's reasonable. So let's talk about this. How do we do this? There are a whole bunch of ways to go about this, but I want to go about this in a way that, wait, step back for just a moment. We could divide this quadrilateral into 2 triangles. And we know that the sum of the angles of those 2 triangles is 360 degrees. And we go, okay, well, okay, 360 degrees for the interior angles of a quadrilateral. Let's call those W, X, Y, and Z. Then the exterior angles are 180 minus W, 180 minus X, 180 minus Y, and 180 minus Z. And if we add those together, we get 720 degrees minus the sum of the interior angles. And if the sum of the interior angles is, like we said, the sum of the angles of 2 triangles when we triangulate, then we get 720 degrees minus 360 degrees, which is itself 360 degrees. So that's one very reasonable solution. But here's one that's kind of fun. Let's suppose that Wendy is out at a park and Wendy has a pet. What type of pet does Wendy have? Maybe she has an emu. And Wendy is out walking her emu. Here's a little leash and a very large bird. And Wendy walks around the park. The park is shaped like this quadrilateral here. Well, she walks, she takes a pathway that leads her to this point right here, and then she turns. And then she walks down a sidewalk here, and then she turns. And then she walks over to the garden, which is over here, and she turns. And then she walks down to the water fountain to get some water, and then she turns and she walks back to where she started. So how many degrees has Wendy turned?
$360.
360, exactly. She's spun around one time, and that's it. She always faced the outside. She could not have spun around twice, but she is facing the same direction that she started out facing. So all is good. And Wendy has successfully walked her emu. Any questions or thoughts about number 9?
I was really cool to say I checked the answers. No one put 720. A lot of people put 360, but maybe worth explaining why the answer is not 1080. I saw a few that were that.
Okay, 1080. Let's see, where would 1080 come from? Is that the sum of the...
Okay, guilty. I could say I did that one. Actually, I got a bit confused because when immediately I heard exterior angles, I didn't know whether you meant like how you did it right here or the total exterior angle.
Understood. Yeah, I just realized
I
that.
just took the most common quadrilateral I know, which is a square. The exterior angle for that, like the total would be 270. So times 4, that's how you get a 1080.
Okay, yeah. This is not the definition of an exterior angle. This is right here. So yeah, this is just, go ahead and take the mistake as learning the definition of an exterior angle. It's not that whole angle around, it's just this one right here. And I think that's in the packet handout. I know that was a whole lot of reading. Yeah, don't stress too much about getting this one wrong because of that definition. Otherwise, 1080 would have been correct for that entire, the 360 minus the interior angle. Okay. Well, let's talk about number 11. And this is a proposition that is easier to believe in than it is to prove when you begin geometry. And I put it in here because I noticed that when we were working problems a couple of days ago, that there were people who were trying to make a leap across parallelograms and say, opposite angles were equal or something like that. Trying to invoke parallel lines, but trying to invoke like two pairs at once, even though that wasn't a theorem that we had demonstrated or held or anything like it. It wasn't the postulate that we were working from. So let's take a look here. Now I'm going to go ahead and just draw parallel lines as if we extended them already. But in green, I'll draw parallelogram. Vertices A, B, C, and D. This line parallel to this one. This line parallel to this one. Prove that the opposite angles of a quadrilateral must be congruent. Okay, well, if we start with this one right here, well, we know that this line CD, is a transversal to line AD and line BC. And so we can say the corresponding angles are equal. So those two angles right there are equal. Then we can say, hey, line BC is a transversal, which intersects lines AB and line CD. So then that, well, actually, we can jump straight toward this angle right here is an alternate interior angle to the angle that we marked at C. And now we can see that angle B and angle D are the same. And really this generalizes. We could have written the same proof if we had started with this angle at A right here, transferred it to that angle at D right there, and then used alternate interior angles right there. Any questions or thoughts about this one? And this proof was short enough that I put it into words just verbally here. But the words that I made verbally would be just as good if you'd written them word for word. Any questions or thoughts about any of these problems or any of the first two handouts? We didn't cover the third one yet. We'll cover congruent triangles on Monday. But any questions about anything that we've covered? Okay, great. I hope you enjoyed the problems, and I'll see you all on Monday.
Thank you, Mr. Crawford.
Thank you, Mr. Crawford, Ms. Wendy.
Thank you.
Bye. Have a good weekend, everyone.
Same to you. Bye.